Welcome to Calculus. Today we will investigate differentiating inverse polynomial functions. We'll take a look at 3 examples. So we'll start off with a simple linear function. Here we're looking at f of x equals 2x minus 1. And our task is to find the derivative of the inverse of f of x. So if you've got a function and you can actually write the inverse, one strategy would be simply to do so, and then once I have the inverse function, take its derivative directly. So for this one, that's the strategy that we'll take. I'm going to start by writing the inverse of this linear function. So to do so, recall I'm just going to switch out f of x with y so that the notation's less cluttered. And then to write the inverse, I need to switch the x and the y. So for y, where y is now, I would write x, and where x is, I would write y. And that is in fact the inverse. So we could use at that point implicit differentiation, but I can go ahead and solve for y, and we can just differentiate as normal. So I'm going to solve for y by adding 1 first, and that will give me x plus 1 on the left equals 2y. And then simply divide by 2, and that'll solve for y. I do need to distribute that 2 there on the left. So our inverse function, which is going to be y, which I'll call the inverse of f of x, is going to be given by 1/2 x plus 1/2. Now once I have the inverse function of f of x, all I have to do to take its derivative is apply my derivative rules. So at this point, we'll just bring this up, and we'll write here, just so we can see it again, the inverse is 1/2 x plus 1/2. So for me to take the derivative of the inverse, I'm just going to apply my differentiation rules. So the derivative of 1/2 x is going to be just 1/2. And then the derivative of x, remember, of the linear term is just 1, plus derivative of 1/2 is 0, and that reduces down to just the constant 1/2. So that was a simple example of writing the derivative of the inverse of a linear function. Let's take a look at an example involving a square root or a radical. So again, I've got a function f of x equals square root negative 4x plus 5, which can be converted over to its inverse pretty easily. So again, we're going to take those same steps. I'll start off by calling f of x y equals the square root of negative 4x plus 5. And then to make the inverse, just as we did with the linear example, here with the square root, we do the same, switch y with x, and then also switch x with y. And the relation we've got there in red, x equals square root negative 4y plus 5, is in fact the inverse. To make it graphable and to apply our derivative rules, I'm just going to solve for y. So for this one, I see that the square root is over that whole right side, so I'm going to cancel it by squaring. Then I also have to square the left side. So that gives us x squared on the left equals now negative 4y plus 5 on the right. So now I can move the 5 and the negative 4. I'll subtract 5. And we'll get x squared minus 5 on the left equals negative 4y on the right. And then to solve for y there, I'll just divide by negative 4 and distribute that to each term. So for our inverse, what we'll get is y. I'll put that is the inverse of f of x, negative 1/4 x squared minus 5/4. So just like we saw with the inverse of the linear function example, now I can apply my derivative rules to take the derivative of the inverse of f of x. So again, I'm just going to write that so we keep it in view. Negative 1/4 x squared minus 5/4. So the derivative of the inverse will appear just by applying our rule. So the constant coefficient stays, negative 1/4. Applying the simple power rule, the old power of 2 comes down as a coefficient. And then x to the power of 2 less 1. And then the derivative of minus 5/4 is going to be 0. And that would reduce down, if I cancel the 2 and leave a 2 in the denominator, negative 1/2 x. So those are two examples where we were just trying to take an equation for a function, write its inverse, and then take the derivative of its inverse. Let's also take a look at an example where we want to write the equation of the tangent line to an inverse function, given the original function. So here we've got f of x equals 4x squared plus 5. So now we're looking at a polynomial equation. And what I'm interested in is writing the equation of the tangent line to the inverse of this polynomial when x equals a, and our a value here is 9. We are assuming that this is going to be for x values that are greater than 0. Remember, this is not a one-to-one function to begin, so we're restricting the domain so that it is one-to-one. Let's start the way we did with our first two examples. I want to write the inverse function for f of x. So just like we did, we'll start with the same steps. I'll call f of x y to reduce the clutter. And then I'm going to write the inverse by exchanging the domain and the range. So where y was, the old range becomes my new domain x equals 4. My old domain x becomes my new range y squared plus 5. And then I want to solve so that that is a manageable inverse. So I'll subtract 5 from both sides. On the left, we have now x minus 5 equals 4y squared. Then I'm going to cancel that coefficient 4 by division. And I'll distribute it to each of the terms on the left. So now what we've got is 1/4 x minus 5/4 now equals y squared. So the last thing to cancel is the square. So we'll apply the inverse operation, the square root. And that really gives me my inverse now. So the inverse to f of x, which is equivalent to our y, is the square root of 1/4 x minus 5/4. So we've written the inverse. So at this point, what we want to do is find the derivative of that inverse. So let's begin that just like we did. So up till now, our steps have not changed. In fact, a lot of this is going to remain the same until we are dealing with the specific a value or x value of 9. So I want to take derivative of 1/4 x minus 5/4. And just to help see how we're going to do that, I'm going to convert the square root to a power of half. In fact, let me do that on the previous step. So that I can apply the simple power rule and the chain rule. So for the first part of the chain rule here, I'm going to bring that half power down. I'll leave the composed function 1/4 x minus 5/4 intact and bring the power of a half down by 1. And then I need to take the derivative of the composed function, which is going to be simply 1/4 times 1 plus 0. Okay, I'm going to simplify that. So this becomes simply a half, but I see I've got a quarter multiplier there. The 0 is going to fade away, and then the parentheses will also fade away, leaving just 1/4. So if I combine that with multiplication to 1/2, half times a quarter is going to be 1/8, times that composed function, quarter x minus 5/4 to the power half minus 1 would be -1/2. So we could write this as a rational function 1/8 times a quarter x minus 5/4 to the power of positive 1/2. So if we had just been trying to write the derivative of the inverse function, we would be done. That's complete. But what I'm interested in is writing the equation of the tangent line to the derivative of the inverse at x equals, in this case, 9. So I need to get the slope of that function. So let's do so. I'll switch colors here just to say we're kind of switching to another task. I'm going to find the value of the derivative of the inverse at 9. So to do so, I'm just going to substitute 9 for any x. So that's 1/8 times 1/4. Instead of x, I'm going to write times 9 minus 5/4 to the power of half. So at that point, I've got really this stuff on the inside of the parentheses to simplify. So 1/4 times 9 is going to be 9/4. And then 9/4 minus 5/4 is going to leave 4/4, which is just 1. And then the square root of 1 is just 1, which is 1 to the power of half. So that reduces down to 1/8 times 1, which is just 1/8. So I'm going to box that because that's the slope. That's the slope of the tangent line to the derivative of the inverse. So now thinking about coming up with the equation of the tangent line, at this point what I need is a point on the inverse of f of x that is defined for both x and y that I can plug into the point slope form. Let me set forward that point slope form so we can see what we need. So that's y minus y1 equals m times x minus x1. And just kind of taking stock, I see that my m is given by the 1/8. So we've got the slope. What I need is an x1, y1, a point that is on the graph of the inverse of f of x. So to do so, I know that my x value is 9. What I need to find is the y value. So let me start to build that. My x1 is going to be 9. Again, that's given as my a. So what I need to calculate is what's y1. So to do so, I'm going to bring this inverse function. So before we took the derivative, and I want to calculate what's the inverse at 9 for f. So it's going to be a similar calculation to what we did for the slope, but now just on the main level instead of in the denominator. So it's 1/4 times 9 minus 5/4, and we've really done this calculation already. 1/4 times 9 is 9/4. 9 minus 5/4 is 4/4, which is the square root of 1, which will just be 1. So we end up having this point 9, 1. Well, we're ready to fill in into our point slope. So I'm going to just overlay here. So y minus my y1 we just found was 1. That equals the slope we found from taking the derivative of the inverse. So that's an 1/8 times x minus my x sub 1 is going to be 9. So that is ready to solve, put into slope-intercept form. So I'm going to distribute this 1/8 into the x minus 9. And what that'll give me is y minus 1 equals 1/8 x minus 9/8. And then last step here is just to add 1. But I'm going to call it 4/4 there on the right side. And that'll finalize it for us. We get the equation y equals 1/8 x. And then negative 9/4 plus 4/4 is going to be minus 5/4. And that completes that task. What we've written is the equation of the line tangent to the inverse of f of x at x equals 9. Thanks for joining for this investigation of finding derivatives of inverse polynomial functions. See you soon.